Hi, welcome back. Today we're going to talk about a special type of variable force. It's the force exerted by a spring as it's stretched. So let's go ahead and get started. So springs obey something called Hooke's law. And through some experiments, a guy named Hooke, he's from the same era as Isaac Newton. In fact, they didn't like each other very much. Hooke said that Newton stole all his work, and it turned out that Hooke was a liar. But he gets this law named after him. So what it says is that the magnitude of the force exerted by a string is proportional to the amount it's stretched. So if you take a rubber band, you stretch it a little bit, it pulls back a little bit. You stretch it more, it pulls back even more. You keep stretching it more and more, it pulls back harder and harder and harder until it breaks. Okay, so the way that it's written out mathematically is the force exerted by the spring is equal to minus, because this is a direction, means that the force is pulling back instead of pushing, times some constant, that's how stretchy the spring is or how springy it is, times the amount of stretch from where there's no force applied on it. It's called from its equilibrium point. Okay, so the x is how far it's stretched. And again, the negative sign, that just means it's the force is pulling back instead of aiding you in the stretch. Okay, so next up, well, here's a pictorial of what happens. Here's an unstretched spring, or a spring that's in equilibrium. We add 1 unit of weight and it stretches a little bit. We add 2 units of weight and it stretches that same amount again. Okay, so it stretched 1 unit here, stretched 2 units here, 3 weights, 3 units, 4 weights, 4 units, 5 weights, 5 units, 6 weights, 6 units. Okay, and if we were to graph this, the slope of this line right here, and if we were to make this an actual graph, and this was force, and this was displacement, the slope of this line is equal to K. Okay, so it would be force divided by the amount of stretch. So force divided by the amount of stretch is equal to K, which is the spring constant. And the units are newtons per meter of stretch. How many newtons to make it stretch 1 meter? Okay, so hopefully that helps visualize what this spring stuff is looking like. Okay, another graphic of the same sort of thing. So we have a spring, it's at equilibrium. We have a spring, it's at equilibrium, and we're going to stretch it a distance x. Okay, so we've stretched it a distance x, and the spring is pulling back with a force of F sub s, or spring force. Okay, and according to Hooke's law, the spring force is equal to the coefficient, or the spring constant, K times x, and it's negative because of the direction. And there's our graph. Looks similar to what we did on the last slide. And if you remember from previous topic, the one on variable forces, the area under the force distance curve, or force displacement curve, is equal to the work. Okay, so the area of that triangle is minus 1/2 kx squared. Well, where does that k come from in the x squared? Well, if we write it out like the area of the triangle, so work is equal to 1/2 the base, which is x, and the height, well, that's force, but the Hooke's law says that the force is equal to minus kx. So if we combine this all together, we end up with 1/2 kx squared, and the force is opposite the direction of the stretch, so it's minus negative work. So that's how this works. When a spring is stretched or compressed from its equilibrium position, it does negative work, since the spring pulls opposite the direction of motion. And the work done by the spring, again, I'm being very insistent that it's the work done by the spring, is minus 1/2 kx squared. Okay, the work is in joules. K is the force constant or the spring constant of the spring. It's in units of newtons per meter, and x is the displacement from the equilibrium. The force doing the stretching, in other words, your pull, is equal to the magnitude of the work done by the spring, but it's positive. You're applying a force in the direction that the spring is stretching. So you do positive work, the spring does negative work. Kind of sounds like gravity, except springs go in two directions. Okay, so the work applied does negative the work of the spring, which is 1/2 kx squared. Here's your multiple choice. Welcome back. We'll do a couple of sample problems here before I give you your free response. So we have a spring that has a force constant, or a K, of 250 newtons per meter. It's initially at its equilibrium length. How much work must you do to stretch the spring 0.05 meters? Okay, so we have a K. K is equal to 250 newtons per meter. Okay, and the work must you do, so that's going to be negative the work done by the spring. We'll call this the work applied here. And that's equal to a 1/2 kx squared. And let's go ahead and substitute in our numbers. 1/2 times 250 times 0.05 squared. So I'm going to put parentheses around the 250. Just keep that straight. Okay, bring out the handy dandy calculator. So we have 0.5 times 250 times 0.05 squared. Enter that. And the work you did stretching the spring is 0.313 joules. How much work must you do to compress it by this? Well, springs are linear. They take just as much work to compress them as they do to stretch them. So you are still doing positive work because you're pushing on the spring and the spring is moving in the direction that you're pushing. So it's still equal to 0.313 joules. Let's try another. Takes 1,000 joules of work to compress a certain spring 0.1 meters. What is the force constant of the spring, or K, the spring constant? Well, the work done compressing the spring is equal to, now again this is the work done by you compressing the screen, so equal to 1/2 k x squared. And we're looking for k. So k is equal to 2 times the work over x squared. So let's go ahead and substitute our values. So we have 2 times 1,000 and that's over, I'm sorry, that's not equal to yet, 0.1 squared. Let's go ahead and pull the calculator up again, see if that helps us out. Okay, so 2 times 1,000 divided by 0.1 squared. And that's 200,000. 200,000 newtons per meter. Sorry about the handwriting, my pen is acting up a little bit. Okay, pressing on here. To compress the spring an additional 0.1 meters, does it take 1,000 joules more, less than 1,000 joules more, or I'm sorry, more than 1,000 joules more, or less than 1,000 joules more? Verify your answer with a calculation. Well, if we square the number, it's going to become larger. The amount of work needed to compress the spring an additional 0.1 meters is going to be more than 1,000 joules. At least that's my estimate. So let's go ahead and try this out. So the work is equal to 1/2 times 200,000 times, well, we're going to now compress at 0.2 meters. 0.2 squared. Let's go ahead and pull up the calculator again. So it's going to be 0.5 times 200,000 times 0.2 squared, and that's equal to 4,000 joules. Not only is it more, it's 4 times more. Okay, if you double the distance, you quadruple the work. Not too shabby, huh? Okay, we have 3 identical springs, X, Y, and Z. They're hung as shown. When a 5 kilogram mass is hung on X, the mass descends 4 centimeters from its initial point. When a 7 kilogram mass is hung on Z, how far does the mass descend? Okay, well, let's use X to find the spring constant, and then we can work on the YZ composite. So, to find K, we're going to use Hooke's law. So force is equal to minus Kx okay, and so this is the force of the spring. So let's see, the force is going to be the weight. We're going to pull on that with mg. So that's going to be mg, and that's going to equal minus k times the displacement, which is 0.04. Okay, so k is equal to mg, 5, and I'm going to use 10 for g to make life easier, over 0.04. Okay, now let's go ahead and pull the calculator up again. So that comes out to 50 divided by 0.04. And enter. So the spring constant is 1,250 newtons per meter. Now, let's take a look at our system here. Spring Y has a force acting on it down by spring Z, and spring Z has a mass suspended on it of mg. Newton's third law says that whatever is pulling Z down is also going to be pulling Y down. And it's going to be pulling it down equal to the mass of the suspended, the mass is suspended, times gravity plus the weight of Z. And we're going to assume that Z has negligible weight. Okay, so that means that the force on Y is mg, and we're going to find out how far it stretches using Hooke's law, K times X. So the force acting on the spring is mg, which stretches it a distance x. So x is equal to mg over k, which is equal to 7 times 9.8. Let's use 10 again. Let's be consistent with 10. 7 times 10 over 1,250. And that's equal to 70 divided by 1250. Oop, made a mistake. 1250. Okay, well that just didn't work out, so I'm going to clear it and try all over at 70 times. No, it's not 70 times. 70 divided by 1250. Enter it, and it's going to be 0.056 meters, which is 5.6 centimeters. So that's just the stretch of Y. How far is Z going to stretch? Well, the force acting on Z is mg, has the same K, same mg, so it's going to stretch another 5.6 centimeters. So X total is going to be equal to 11.2 centimeters. And that's for this spring that we would call that spring is in series. So the stretch is greater. So if we were to calculate an effective or an overall spring constant for this, it would be different than 1,250. It would be 70. Okay. 70 is our weight, or the force exerted on it, divided by 11.2 centimeters. And let's see what that is. 70 divided by 0.112. And our effective K now is 625 newtons per meter. Notice it's 1/2 of the spring constant for a single spring. So when you chain your Rubber bands together, you have to pull on them less to make them stretch. Yeah, that's kind of interesting. It's kind of counterintuitive. You would expect that you would have to pull harder if you stuck two of them together. Okay, let's go on here. Okay, so here's a little bit of a diagram of springs in series, and then this last one here is a spring in parallel. So if we put a weight on one spring, it stretches a certain amount. If we put the same weight on two springs, it stretches even further, which means that the spring constant is less. Smaller spring constant, much more stretchy. However, if we connect them in parallel, it's as if each one is supporting half the weight. Well, really, they are supporting half the weight. So it appears as if the spring constant is less. It's one half of what? Or, I'm sorry, the spring constant is more. It's less stretchy. It's twice as stiff as a single spring. Here's your free response. Good luck. We'll see you next time.